So CCRi is a data science and software development company that's been around for a couple decades in Charlottesville. And I'm going to talk a little bit about some of the work that I've done very recently in the past couple weeks even, and then Courtney will follow that up with similar work. So we often deal with problems where you, well, this applies to lots of different domains. You have a geographic area and you want to search for something like, maybe I want to find a place to open a new pizza restaurant, maybe I want to find a way to curb crime in a given area or a specific type of crime. So we have a lot of different data. So we have lots of different data and lots of different places, and we need to make it work together. So I'm going to talk about doing that using the city of Chicago as an example. So I used Chicago because Chicago has lots of different ways to get data. I guess there's I don't know if anyone knows about it, but there's a data portal for Chicago, and you can get just about anything you want for the city of Chicago. Wikipedia has lots of geotagged articles for Chicago. There are, you can get OpenStreetMap data, which you can get for most places in the country, and satellite imagery was easy to get. But for all of those things, there's lots of different data types. So the Open Data Portal for Chicago has lots of shape files. You can get like the L train shape files. You can get major roads. You can get parks, farmers markets. In shapefile format, you can get lots of flat files. So you can get like a lobbyist registry if you're looking at, say, voter information. You want to do some sort of political analysis. You can get food safety violations if you want that. There's building violations. I'm going to talk about crime events. You can get those text descriptions, which I got from Wikipedia, and then the satellite imagery, although images could also include if you wanted the, say, geotagged Instagram photos. Okay, so all of those things come in very different formats. Most of the machine learning algorithms we use require everything to be in the same format, which is usually just one long vector of numbers for each entity that I care about. So a shapefile obviously isn't going to work. Imagery doesn't work. So one thing that I can do with all of them is turn them all into triples. And if you're not familiar with triples, what I mean by that is if you follow some of these arrows, say if you start at Manila Airport, has land use, transportation, there's a triple. If I go Manila Airport is within Manila, that's another triple. So one thing I can do with all these triples is I can take all of my data in its very different formats, transfer them to triples, and then I can put the triples in a different machine learning algorithm to turn them into embeddings, which I can then use in traditional algorithms on, like logistic regression. So we'll start with Wikipedia. So this is the outline for Chicago. I had this question the other day, that bubble up there, so you don't get fixated on it, the weird little satellite on Chicago is O'Hare Airport. And that cluster of Wikipedia articles is kind of where the loop area is, where all the main downtown business center is. So we have 1,652 articles for places around Chicago. I only use the ones that are actually within the border, but the green dots are all the ones in the Chicago area. We took those documents and did sort of like a word-to-vec magic on that and got embeddings for those. Now I have embeddings for documents, but that's still not going to work with my shapefile data. I needed it to be a triple. So what we did is we found the nearest neighbor, 6 nearest neighbors, for each Wikipedia article. And now I have a triple. So as an example, my first article is similar to my 4th article. And here's a quick example. You don't need to read it exactly, but these two things are both articles that talk about libraries. So as a sanity check, I've identified 2 similar Wikipedia articles. All right, then we got imagery. So that is imagery for all of Chicago, and there are little tiny dots on there which represent crime events. And the only reason why that's relevant is because often in areas that we're interested in looking at in the world and that we want to learn things about, we don't always have all the imagery we want. So for our purposes, I subsetted this. So I used the crime events to subset and only looked for images where there was a crime event, but I only used 5,000 of the crime events. We downloaded the imagery, and then you have to chip it up into little pieces. I'll show you what a close-up of that looks like. So this is O'Hare Airport, where there were something like 12 crime events, and that little red box there has 5 crime events in it, so we took just that chip. And Colin Cassidy did me a favor and talked a little bit about how we turn those into embeddings. So we take each of those images, which still aren't a triple format, I still want a triple, ran it through VGG19, and got embeddings out of that, but I still don't want a vector yet. So we find the 10 nearest neighbors for any image, and then now I have a triple again. So image 1 is similar to image 7, as an example. And this, I could show you lots of these, but basically the roads, 2 roads, good to go. These are 2 similar images. Okay, now I have my crime events. This is about 300,000 crime events over 15 months in Chicago. They're all different kinds of events, and the data set includes, like, was someone arrested, were they not arrested? Most of the data in the crime data set is basically another proxy for location, like ward or district or police beat. And I wasn't interested in that, but I was interested in what the primary type of crime was, which included things like arson, narcotics, assault, robbery, car thefts. So I want to use these points, and I want to use what type of crime they were, and it is not clear how I make a triple out of that yet. So we're gonna leave that for a second. Then I had OSM data. So these are my OSM points. There are about 900,000 of them. There's a zoom in of the loop area right there. So you can see that everyone is a polygon, and they all have attributes. So the attributes that we cared about were amenities and what building type. So amenities were things like, did it have, there was one that was like waste bin, amenity restaurant, cafe, parking, and then the building types sometimes just said yes, but they had things like churches, mausoleum was an interesting one, house, apartment building. So I want to use that. So we had crime events, and we have the type of event they were, and we have OSM data where I know that it's a building, and it's an apartment building, I know its location, it has amenity parking. What do I do with that? So we created Voronois. So essentially, this is just a way to cover all of the area that I'm interested in tiny little polygons that I can use to bring my data together. I used OSM to make these, so it's essentially an algorithm that will make smaller polygons where the data is denser and bigger polygons where it's not as dense. So O'Hare Airport up there has pretty big polygons because it's basically one thing. And then the little tiny polygons are denser areas of population or business. I used a mean square area of 2 kilometers, so they're fairly small on average. Okay, now what do I do with those? I still need triples. So I have my crime data, and I can say, okay, this Voronoi has crime type robbery. And now I can tie my crime data in there. This Voronoi has amenity graveyard, which is an interesting amenity. Voronoi 1 has building school. So this particular Voronoi, so one little polygon, has all of these things in it. I also need to get my Wikipedia and imagery data tied in there, because right now they just say Wikipedia is similar to Wikipedia, and I have image is similar to image. So I have to tie those geographically to my space. So I've got this Voronoi contains this Wikipedia article, and this Voronoi contains this image. Now, this is my little graph. This is what I wish I had a pointer for you, but if you can follow this, my Voronois are in blue. So this is just an example. I've got 2 different Voronois. They have in common that they both have a church. One of them has an office building. They have in common that there were assaults in each of them, but only one had an arson event, or multiple arson events possibly. Voronoi 2 has image 1 in it. Voronoi 1 has image 5, and those 2 images are similar, just like the Wikipedia. Each one has a Wikipedia article, but those articles they have in common. So hopefully you could follow that. So that's my little graph of what's going on here. So I'm going to take all those triples. I threw them in Transy, which Courtney will talk about, and I get embeddings. So for each entity, so my Voronois, for example, I end up getting, in my case, a length 100 vector to describe it. So I have 100 features, numbers that I can then put into logistic regression or random forest or whatever I want. Okay, and as a sanity check, I'll go through this kind of quickly. I now have all of my entities, all my Wikipedia articles, Voronois, in 100 length vectors, which I can't visualize, so you might be familiar with t-SNE. It's just a way to collapse it into 2 dimensions so I can see the structure of the space because I can't visualize 100. So what I want to see here is that things are clustered together. So the green is all the imagery is together. That's good. My model is able to identify images. The Wikipedia articles are the red part. You can see that some of them are clustered together a little bit because they, in theory, are similar articles. The point is just that I see clustering, so I know my model learned something. All right, so just as a quick example, what I can do with that now that I have it, dentist office is an amenity in OSM, and so I just predicted, I used a quick decision tree, and I predicted which Voronoi cells contain dentist offices given the ones that I know have dentist offices, and I just did a regular old 80-20 test train split, and then predicted dentist offices over the whole space. The ones that are green are the ones where there really are dentist offices, and the redder they are is where the model predicts that there should be a dentist office. And what you could do with that is, for example, if you look over by the little loop area, you can see there's a couple of very dark Voronois that the model thinks should have dentist offices, but they don't according to OSM, which contains many errors if you've ever dealt with it. If you Google this, if you wanted, zoom in on the loop, whether there's dentist offices there, and there actually are dentist offices in those areas that just weren't labeled in OSM. So just as an example use case. That's it for Chicago. Courtney is going to move on. She'll talk a little bit more about the embeddings, and then she'll tell you what she's done in a similar fashion.
I'm Courtney, and I'm going to pick up right where Taryn left off and talk about some of the cool applications of machine learning tools to this fused data space that we just worked hard to get. So the first thing to talk about here is how to go from the entire set of all of these triples that Taryn just described, which we call the graph, to something called embeddings, which you've now heard that word several times. All an embedding is just a vector of numbers in the dimension of your choosing. So you could have a 3-dimensional embedding vector, a 10-dimensional embedding vector, or if you're Taryn, maybe you're working in a 100-dimensional embedding space. But the important thing here is that we're just talking about a bunch of numbers. We're representing all of our entities and relationships in our data as a bunch of numbers. Why do we do this? Two main reasons. One is that this turns out to be a very compact and efficient way to represent a ton of information that we just worked very hard to get. And the second is that all of our fancy machine learning tools really just want a bunch of numbers as input. So if we can represent our data that way, then we should. So to talk for a minute here about how we decide what those vectors, what the numbers in the vectors actually are. Typically at CCRi, we've been using a lot of translational models, specifically TransE. What TransE tries to do, you can think of in terms of vector arithmetic. If we have embedding vectors representing, let's say Peter is an entity, and we know that his boss is Jane, so maybe we have the example triple, Peter reports to Jane. We want to be able to add the vector for Peter to the vector for reports to and arrive at Jane. And then what we want is to take that same vector representing reports to, and when we add it to Thomas, we also want to land at his boss. And maybe his boss here is Mary, if you have learned a good embedding space. So that's a general idea of what we're doing with TransE. And so here's a visual that isn't working. This is meant to be a GIF of what it means to learn embedding space. And when this is working, what you see is we basically start by randomly initializing all of the vectors. So they start in this kind of overlapping state here and separate out into nice little clumps of things. So two things that you would see. One of them is things that are similar to one another, maybe all the types of birds or the types of sports. If they are actually similar things, then we want them to be close in embedding space. We usually just use Euclidean distance to represent that. The second thing is that the relationships that exist in your data, you also want those to exist in embedding space. And so that's a key thing to remember, is that your relationships between entities in your data are represented in embedding space. So this is another GIF, but this one's okay that it's not working, because this slide is about what you should not do once you arrive at a learned embedding space. And that is, so here, this is a 3-dimensional embedding space, and we'd be like clicking around, and it looks really cool, and we're investigating it visually. But some reasons you don't want to do that are that you don't really learn any valuable information from it, although it is really fun to look at. But you also can't do this well outside of 2 or 3 dimensions. And we really want to be working in, I don't know, maybe 42-dimensional embedding space. All right, so what do we want to do? We want to use machine learning. So finally, we have arrived. We are going to open up our machine learning toolbox and use some cool techniques. So for the remainder of this talk, I just want to go through 3 examples of both supervised and unsupervised techniques that we've been using to uncover what our data can tell us. Now, before we go on, just to quickly review, when I say supervised machine learning techniques, this just means that we have a labeled set of training data. So we label according to what we know is true, some of the training data. We hand that over to a model, and the model learns what is true, and we use that on all the other data it hasn't seen yet. When we say unsupervised machine learning techniques, what we're talking about is there's no labeled training data. We simply hand the model all of our stuff and ask it, is there anything interesting going on here? So with that distinction in mind, let's jump into a couple examples. So one thing we might want to do is something called similarity search. And the general idea here is that you want to ask the question, given one thing I'm interested in, what is the most similar thing to it, or most similar other entities, plural. So here for this example, our data sets are vessel metadata, things like how big is a ship, maybe what is its maximum speed, and then also track data. This comes from AIS. Which just represents locations of commercial vessels over a certain period of time in the area of your choosing. So if we merge those 2 data sets in the way that Taryn described, and then we ask Embedding Space, what is the most similar vessel to the Norwegian jewel? That is the same as saying, what is the closest thing in Embedding Space to the Norwegian jewel? The Carnival Elation. This is a good top hit. This is something you want your model to be able to tell you. And I will also concede that this is probably a solved problem. We know that these 2 vessels are very similar. However, this is a good introduction to more complicated questions that we can ask and answer using Embedding Space. For example, what are all the major sea lanes that large vessels use leaving the port of New Orleans and coming back to it? So we could go look up all of the large vessels in our data and try to track down their track information. Or we could leverage the fact that we have already munched together all of this information into Embedding Space. And instead, what we'll do, and what we did here, is to say, what are the 30 most similar vessels to the Norwegian jewel? Find those in Embedding Space, take their tracks, and turn them into a heat map. And that is the orange heat map that you're looking at here. And so what we get by asking about one thing in Embedding Space is we get an entire activity pattern for a class of vessels. So this is a pretty powerful tool. So moving on, another common technique, also in the world of supervised machine learning, is classification. There are several ways to do this. Most frequently at CCRi, we've been using random forests. These are ensembles of decision trees, which is depicted on the right here. But the general notion is we want to label a set of training data according to some classes that we're interested in, train a model to be able to recognize those classes of things, and then pass all of our other data through that classifier. So to set the stage, we're in New Orleans right after Hurricane Katrina. Disaster relief effort is going on, and we would like to identify candidate food distribution centers across the entire city. So we're looking for buildings that can hold a lot of food and that can distribute that food to localized regions until the city stabilizes. So the first thing that we do is to take our different disparate data sources. In this case, we used OSM, OpenStreetMaps, and overhead imagery. We make triples out of all that data, and we also discretize the physical space by making a Voronoi covering that you see here. And then the next step is to create the training data. So what you see in green here are you walk through and you find a handful of examples, and we label certain buildings as this will probably make a good distribution center. Something like the Superdome is very large, can hold a lot of food, or the Saints Training Facility, also large and near big highways. We hand that training data over to the classifier, we train it, and then we pass all the other Voronois in our space through this classifier, and we end up with what you see here in red are the areas that the classifier has nominated as good candidates to be a distribution center. So when we're zoomed out like this, looking at the entire city, one nice thing that you get out of this is that there are certain areas where the model has picked up on a lot of good candidates, and you might want to immediately go investigate those manually closer instead of the entire space. So what we've done here is to reduce the physical space you need to look at yourself to a very small subset of that. Zooming in a little bit, we can see some of the things that the model has picked up on in more detail. Sometimes we get large buildings, sometimes we get areas close to highways, and when we get a really good result, both of those things are true. But the key thing to remember here is that this is not a rule-based model. We never told the model, hey, I need a building of at least this size and at least this proximity to a road. It learns that based on the training data that you give it. So if we think about a couple other applications of this kind of technique, if you're in retail, this is very maybe similar to the dental office example that Taryn gave earlier, but maybe you want to open a new location and you care about things like what other businesses are close by and maybe some physical characteristics of the building itself. This is a model that's well suited to that problem. If you're in agriculture, maybe there's a particular crop that you want to grow and you want to grow in new areas. So you're looking to expand. If you have data that captures the things important to your crop, things like the soil acidity and the average temperatures over time and average wind speeds, then you can combine all of that data and use something like this to survey a very large geographic region and quickly find some areas to look into farther. Or a similar problem might be in ecology. You might want to look for areas that are in danger of erosion, maybe right now or in 5 to 10 years. So some cool applications of this type of a technique. Okay, and so the final example here that I'll walk through is in the realm of unsupervised learning. Remember that we no longer have training data that we're working with. We are now just taking all of our data and handing it over to a model. In this case, we are asking the model to cluster our data. So the idea here is to assign each entity in the data to a group, which is called a cluster. Typically, at CCRi, most frequently, we have used the technique k-means to do this. But the important thing is, well, actually, we just heard a whole talk about this. Machine learning in general, but especially unsupervised stuff, it doesn't give you explainability. It doesn't tell you why it did. So bear that in mind as we look at our clustering example here. So here we are back in New Orleans. Well, so we're along the Gulf, really, from New Orleans down to Galveston. And what you're looking at here is a visualization of clustering, and each color in this image corresponds to a different cluster. Now you'll notice that very frequently, sometimes you will get a clustering to correspond to a general geographic region, but sometimes that is not the case, and that's often more interesting and what might give you insight into what's resident in your data. So for example, well, a couple examples we'll pick out here. It looks like we've identified some shipping lanes in and out of New Orleans and also Galveston. That's the red and the pink Voronois that we're looking at here. So good to remember that these are not necessarily related geographically, although they do fall in a line, but rather what's really going on here is where the model is picking up on the behavior of the ships and their tracks that we trained this model on to identify what Voronois are close to one another in embedding space. Another interesting example here is this set of 4 pink Voronois and kind of a sea of purple. What would you expect to be offshore in a Gulf? Maybe oil rigs. So this is an example of how the model doesn't tell you why it did what it did. The reasoning is left up to you, at least for now, although at CCRi we are starting to get into explainability. This is, as you've heard, a hard thing to do. One other example I'll point out is this yellow region seems to be following coastal areas. So I think what the model has picked up on here is that when we're in shallower waters or we're operating close to shore, ships behave in a certain way. And so the model has recognized that and clustered all of these Voronois together. So that's my last example that I have to give to you today. We're doing a lot of cool things at CCRi. Machine learning is great. We're also doing things like automatic labeling of video or information retrieval if you're in the text domain. So if any of this interests you or you want to learn more, we would love to talk with you more about it. But thank you for your time.